Okay, so now in this part, let's start by looking at simple image classification CNN. So this is the schematic that we've been seeing many times already in the slides before, but let's just discuss it a bit more with the context that we have now, now that we understand convolutional and max pooling layers. So we start with a certain input image, and then we have a convolutional layer here. So what that means is that we define a certain number of output channels, and we have independent convolutional kernels which we convolve with this image to get these different output channels. Okay. So okay, here we have a bit more detail. So in terms of like concrete numbers, let's say we are looking at an image which is 28 times 28 pixels in size, and let's say we apply a convolutional layer with a 3 by 3 kernel with a stride 1 with same padding and number of channels equals 4. So recall that if you have same padding and if you have stride equal to 1, this will mean that the output size will be the same as the input size. So if the input is 28 by 28, the output is also 28 by 28. And since we chose the number of output channels to be 4, the entire output size is 28 by 28 by 4. Okay, so now on this output, let's apply a max pooling layer with a 2 by 2 kernel and a stride of 2. So basically we will take each channel and we will apply a 2 by 2 kernel with a stride of 2. So this guy will go from 28 by 28 to 14 by 14, and the same for all of these guys, right? So then we will get uh, uh, a representation which is of size 14 by 14 by 4, right? So the number of channels remains unchanged. And now we will apply a convolutional layer taking this whole thing as input, and we will define a certain number of output channels that we want. So we say, okay, we want number of output channels to be 8 now. So now we will have a convolutional layer with 4 input channels and 8 output channels. And we say, okay, we want a convolutional kernel of size 3 by 3, stride 1, and same padding. So again, due to stride 1 and same padding, we end up having preservation of the input size in terms of this spatial size, right? So this 14 by 14 remains 14 by 14, and then we end up having 8 channels as desired. Again, we apply a max pooling layer, so then this 14 by 14 goes down to 7 by 7, right? At this point, let's say we stop with the convolutional layers, and then we vectorize this representation. So that means basically we uh, take this guy, right, and then put all the rows, all the columns one after the other, right? So that becomes one vector, and we do so for all of these guys, and then stack all of them, right? So basically just convert this into a 1D vector, and the size of this guy will be just 7 times 7 times 8. That turns out to be 392. Right? And then finally, we will have a fully connected layer. Let's say we want to classify this image into 1 out of 10 classes. Then we will have 10 nodes in this output layer. Basically, we would want, if this image belongs to class 3, we would want the third node to be set to 1 and all others to be set to 0. Right? So this vector will represent the probabilities of this image belonging to each of the 10 classes. Right? So this is basically a simple image classification CNN. A good exercise question for you here could be to find the total number of parameters in the CNN, right? So see, we already discussed that there are learnable parameters in this. So by parameters, I mean learnable parameters, right? So the parameters whose values will be randomly initialized and will be then found by the optimization process. Okay, so um, so we have this convolutional layer. So we have convolutional kernels. These are learnable parameters. Biases. These are learnable parameters, right? And then in the max pooling layer, we don't have any learnable parameters. Then again, we have a convolutional layer. So we will have learnable parameters here. No learnable parameters in the max pooling layer. No learnable parameters in the vectorizing step. Okay, this is just vectorizing, right? And then we have a fully connected layer here. So we will have weights and biases here, which will be learnable. So you have to put all of these together and then sum them up, and you will get the total number of learnable parameters. I think this will be a good exercise if you try to do it. Okay. And as another exercise, what would be also interesting is, so far we have looked at classification, but an equally important problem in medical image analysis is segmentation, which means if you have an image like this, you want to assign to each pixel it belongs to a certain region. So here I have divided the image into 11 regions, right? So including the background. So you could think, what could be a segmentation CNN? What could be the architecture? And by architecture, basically I mean what could be the arrangement of different layers, namely convolutional layers, max pooling layers, um, fully connected layers. So just try to think, how can you arrange all these different layers together so that you can have this image as an input, or an image as an input, and as an output you also want an image. Okay. So try to think, maybe pause the video a bit, think for 5-10 minutes, and then later in the lecture, maybe in the next part, we will discuss some segmentation CNNs, and then you can see if what you thought actually matches with what is used usually in practice. Okay. So now we have looked at classification CNN. Let's now look at why are CNNs so well suited for image analysis. So we have mentioned this several times, that CNNs end up producing like state-of-the-art performance for a lot of image analysis tasks. So what makes them so particularly well suited for images? So one is, if we just compare MLPs with CNNs, it turns out that MLPs contain much more parameters than CNNs, and this has a risk of overfitting to the training data, and CNNs are able to avoid that by having fewer parameters. So let's look at this a bit more in detail. So one naive way of using MLPs for image analysis would be to start with an image, which is a 2D matrix, and to convert it into a vector, just vectorize it. And now we have just a vector, and then we could have um, of MLP to do analysis on this vector, right? So one problem with this approach is that we would end up having to use these fully connected layers, and these fully connected layers have a lot of parameters because each element of uh, of the input is connected to every element of the output, right? So we have all these have different weights, and then the second guy is again connected to all of them with different weights, and so on. And then the same for the next layers. So here we have a quick example where we say, okay, let the image be m by n. Then by vectorizing it, it becomes just mn. And let's say this layer contains t1 units. And then recall that in our MLP, you have h1 as w1 times h0. H0 is this guy, plus p1. So if we substitute these numbers here, so if we say the image is 64 by 64, and if we say that we want 32 um, units in this hidden layer, then it turns out that we end up having to have these number of parameters already in the first layer. So this is already a very big number, right? This is just to give you a sense of how this number of parameters really just just goes crazy. It just goes very big because you have this product of m by n, the size of the image here. Okay, so yeah, you can try to do this maybe for a 28 by 28 image. So if you have a 28 by 28 image, and then you vectorize it, and then you have a couple of hidden layers with size, let's say 150, and then finally a size 10, then what is the number of learnable parameters here? And then this is a very nice exercise, I think, because then you could compare it with this guy, which is the CNN that we saw before, which is also taking 28 by 28 and producing 10 by 1, right? And in fact, in fact, it has the same number of kind of hidden layers, because you have one fully connected layer, two fully connected layers, three fully connected. So you have three fully connected layers here, and here you have one convolutional layer, second convolutional layer, and one fully connected layer. So again, you have three layers of processing in both networks, but then you can try to compute the total number of parameters, and you will see that the number of parameters here are really much larger than the number of parameters that you will end up getting here. And to see where this parameter saving comes from, notice that if you had a fully connected layer, if you did not, if you kept the matrix as a matrix instead of factorizing it, what it would mean is you would have connections from all the input pixels to each pixel in the output. Okay, so you would have a weight for this pixel connected to this pixel again connected to this pixel, and so on. And therefore, you would have this mn number of inputs, each connected to each of the outputs. Okay, what happens in CNNs, and this is really the magic, is that you have a small kernel which is like 3 by 3 or 5 by 5 or something, and therefore you need only weights from that small region to a certain region in the output. And importantly, you slide this kernel through the image, keeping its weights fixed, right? So these weights are actually shared by all these input layers, right? This is called as weight sharing, and this brings about the drastic saving in the number of parameters in CNNs as compared to MLPs. Okay, so that's number one. That is why CNNs are well suited for images. The second thing is that images are composed of a hierarchy of local statistics, and CNNs are well suited to leverage this. So what do I mean by this? So what I mean by this is that, if you think of any image, right, it is composed of a certain hierarchy. So then at the very lowest level, you have things like edges and corners. And then if you kind of merge together a few edges, a few corners, a few of these low-level features, then you start getting a bit more complex features. You can generate like circles or, squares and shapes like this. And then by combining further these kind of mid-level features, you can get more complex features. So essentially, um, there is this hierarchy in images, and CNNs themselves naturally can leverage this hierarchy. And this is because, initially in the first layer of the CNN, you have like a 3 by 3 convolutional kernel or a 5 by 5 convolutional kernel, and the CNN sees only a small portion of the image. Okay, but then as we keep having more and more layers, we discussed this while looking at the receptive field, that let's say we have these many convolutional layers, then if we look at a certain pixel here, this pixel is actually looking at this region of the previous layer, but then a bigger region of the previous layer and an even bigger region of the original image. So this pixel here is able to look at a fairly big region of the original image. So what can happen is that the convolutional network can extract low-level features in the first layers, so edges, corners, things like this, and then successively keep building on these low-level features to construct more and more complex ideas and complex understanding of the image. So yeah, CNNs are naturally able to leverage or understand this hierarchy or this multi-scale. They're able to develop this multi-scale understanding of the images due to their basically design, right? And then the third point is translation equivariance and approximate translation invariance. So let's first try to understand what is equivariance and invariance. So when do we say that a function is equivariant with respect to a transformation? We say this when applying the function on a transformed version of the image or some input is the same as transforming after applying the function on the input. Okay, so that's just equivariance with respect to a certain transformation. And invariance with respect to a certain transformation means that applying f on the transformed version is the same as applying f without any transformation at all, right? So that means that applying the transformation on t does not change the effect of f, uh, the effect that f is going to have on x. Okay, so let's see how these are important. So translational equivariance means that if I have an image here and if I have a certain segmentation of that image, now if I translate this image, just if I move it upwards, then the segmentation should also move upwards, which means that I need to have translation equivariance if I want to solve this problem properly, right? So it turns out that CNNs have inbuilt translation equivariance because of the convolution operator. So the convolution operator, for example, here is extracting edges. Now let's say I move this image a bit, then apply this convolution operator. The extracted edges will also move accordingly, right? This is because this is a small filter which is applied all over the image. And if I translate this image, I can still apply the same filter all over the image, and I will get the corresponding activations um, in the translated image. The corresponding activations will also be translated, right? So translation equivariance is thus inbuilt in CNNs. What is also desirable sometimes is to have translation invariance. What that means is, suppose if I'm doing an image classification problem, and if this image of the eye it corresponds to a certain severity of this diabetic retinopathy, then if I just translate this image a bit, I should still get the same output. So then here due to the translation, the output does not change at all. So this is translation invariance, right? Uh, and the pooling operation that we have in CNNs lends partial translation invariance to CNNs. And this is because in the pooling operation, we are essentially aggregating information and reducing the dimensionality of the region. So what happens is if I have a certain activation in a certain region, I am going to lose that spatial information when I do a max pooling operation, for example. So, for example, if I have a certain activation at this region, let's say I have a certain activation in this region, okay, and if I move this region by a bit, I might still end up getting the same output after the max pooling step, because the max pooling step can kill those small translations, right? And that's why we have this kind of partial translation invariance in CNNs, right? So so now we only talked about equivariance and invariance about um, uh, equivariance and invariance to translations, but it might also be desirable to have equivariance and invariance to other forms of transformations. For example, you can imagine that the segmentation function should be equivariant to rotation, which means if I rotate my image, the segmentation of the image should also rotate by the same amount. It turns out that CNNs do not natively offer such properties, and then we have to do some other kind of, we have to come up with other ideas to encode such equivariance in CNNs. One of these ideas is data augmentation, which we will look at a bit more in next week's lecture. And there are also other ways to explicitly encode such ideas, not in the architecture of the network itself. And this is, for example, one work which does that. But overall, uh, the reasons why CNNs are highly successful on image analysis tasks can be summarized here. So one is they have far fewer parameters as compared to MLPs. Second is they are able to naturally leverage this hierarchy of local statistics that images are composed of. And the third is that they offer natively translation equivariance and approximate translation invariance. And these properties are useful for image analysis tasks. Okay, so with that, we have looked at this part as well. And now we will stop here and look at the last two parts in the next part of the lecture.